show of hands, who here has ever tried pushing the hot or not button on the website hotornot.com? That's quite a lot. Okay, well, you can thank him. Because he was prior the VP of Engineering of Hot or Not. But he is currently the CTO of Chango. This is Mazdak Rezvani, pardon me. Mazdak Rezvani. And we have with him the founder and VP of Engineering of Operations at Aerospike, Srinivasan. And Srini has 20 plus years of experience, was formerly the chief architect of IBM's DB2 Internet products, and also a former Yahoo Senior Director of Engineering. Please welcome Srini and Mazdak.
Thank you.
Thank you. So I have actually spoken at this event, I think it was sometime in the fall of 2012. And my co-founder, Brian Bukowski, also spoke here, I think, last year. You might have seen some of those talks. We talked a lot about the details of the technology of Aerospike and what it is we are attempting to do. And one of the things that we claimed that we were going to do, or we were doing, was get Google scale technology available for everybody else who wants to be like Google. And we have several customers like that today. We've been in existence for over 5 years. We thought it would be great to have a database on presentation when we invited one of our Google scale customers, Chango, to present technology from their viewpoint. So I'll hand it over to Mazdak.
Thanks, Mr. Can everybody hear me in the back? Great. So, thanks for coming. It's a pretty good crowd. I hope I won't disappoint. But so what I want to talk to you about a little bit about is the challenges that we face as a company in the sort of the new ad tech space, right? So Chango, is one of the many players in this new field of programmatic or real-time marketing or advertising, really. And what we do is we're integrated with what are called real-time ad exchanges. So, for those of you who don't know, every time you are browsing around and an ad loads up, just before that ad loads up, in the 250 milliseconds or less, the ad network, usually some, guys like Google, guys like AOL, actually, guys like AppNexus and so on and so forth, they basically start an auction off in the back end. They talk to 20, 30, 40, 60, I don't know, buyers, and they pass along the packet of information about who the person is that's viewing the ad, and they expect you to come back with a bid or no bid on that person. And what we do, and what we think we do best, is that we help advertisers by having a proprietary data network as well as their own data available for real-time analysis and connection as these bid requests, these ad requests are coming in. So, we have sort of a central, if you will, profile, universal profile is what we call it, of people who we collect data on. Now, this is obviously anonymous data collection, but it is pretty comprehensive. Now, the data comes to us from our own data network that we have across the web. It comes from the advertiser as well. And sometimes, when those bid requests are coming in, we're actually looking up all this different information, kind of putting together, figuring out what the right ad is, what the right campaign is for that person at that very, millisecond, and showing the right ad to them. There is, the breadth of this real-time ad exchanges is really just taken off in an immense way. We started Chango in 2008. By 2010, Google and AppNexus and a few others were in full swing, but now we have inventory across video exchanges. Even YouTube ads are auctioned off in real time. Facebook newsfeed ads, Facebook ads on the right-hand side, and a bunch of other sources of real-time inventory. This diagram is a really high level sort of the kind of three big pieces of how our sort of architecture comes together. So there's the data collection piece I talked about, which is us getting data about people, whether they're browsing on the advertiser's website or whether we're seeing them in our data partner network, performing on-site search, maybe going to a comparison shopping engine, lots of different places. And then sort of parallel to that is the real-time bidding piece, which is really the fire hose of bid requests coming in. And I'm going to throw some numbers at you in a minute. And these two pieces are really, really time sensitive. You're talking about, when you're collecting data, you have, in ad tech parlance, your pixel, which is a piece of JavaScript, on an advertiser's website. The last thing you want to do is, hold that website up, right? So not only JavaScript itself, asynchronous and so on, but even without that, though, you want to come back as soon as possible and just kind of move on to the next request. You want to, one of the key differentiators for Chango is that we want to do all this stuff in real time. We don't want to collect data now, analyze it 4 hours later or 2 days later, and then show you an ad. We think there's real value in reacting to data really quickly because intent changes quite fast, right? I mean, if you're doing research to buy something or somehow know that about you, by the time you're off and 2 hours later, that intent might be gone. You might have already bought whatever you're looking for, so your advertisers lost there. So those two pieces are really time sensitive. The real-time bidding piece, we'll touch on that in a few minutes, is really, really time sensitive. So, and last but not least, all of this activity is generating a ton of data. A ton of data, which we have to store, analyze for analytics. We have to sometimes analyze it for for machine learning and intent analysis as well after the fact. And so there's a whole sort of ecosystem dealing with all that. So when we set out to build Chango's infrastructure, we were lucky to start with this in mind. A lot of our other people in this space maybe grew out of a ad network or a different business. We said we wanted to do real time right the first time, and it definitely was not easy. So the first key thing was data collection had to be in real time, and of course the bidding had to be in real time. There's no two ways about that. We wanted to build an infrastructure that scales horizontally and as few points of failure, as single points of failure as possible. Of course, this was not an overnight thing. There was many failures over the 3 or 4 years, but we have now mostly achieved that. And it's very important again because we have a lot of we're collecting some data from advertisers that we want to be very sensitive to load times, to failures. So should something happen in New York and a disaster strikes, we want to make sure that your San Jose data center takes over and nothing is lost, and your pixels don't go down, so the advertiser is not feeling the impact. Some numbers. So yeah, if you look at the incoming public switches, you're seeing over 2 million packets per second coming in. The actual bid requests per second from our current set of ad exchanges is, above 500,000 per second. So that's the real-time bidding piece. All the activity that we generates about 25 terabytes of data per day, which we need to do something with. At the very least, we just need to store that. I mean, even storing that, when you think about that, that adds up pretty quickly. But we do more than store it. We have to analyze it for lots of different things. So there's a repeated number there, but there's over 6,000 CPU cores that are in our big data system, and 25 terabytes of memory active across a bunch of our clusters, including the Aerospike stuff that we're going to talk about in a minute. So yeah, I mean, speaking just briefly about the sort of data ingestion piece here. As we said, there's two different ways data is coming into our system. First is the first-party, third-party data that's coming in for, so we know something about the person that's sort of doing something on the web. And then the RTB system itself is generating a ton of data, right? People are going from place to place. You're almost seeing a browsing pattern shape up as you kind of go from site to site, and ads are firing up and so on. All that data is stored in our distributed file system for a couple of different purposes. That data is analyzed by an ETL system, saved in our analytics databases. That data is also stored for sort of long-term storage and analysis. Should you need to do that in the future. That same data needs to be operated on by our MapReduce systems for various reasons. One of the biggest ones being the data science team constantly coming up with new algorithms, machine learning algorithms to kind of make sense of some of that data. So that needs to be iterated on. And as I was saying before, there's a whole real-time piece to this that's very important, because as we're collecting that data, we really want to be able to act on it as quickly as possible. And that's why that whole sort of left column there with the real-time processing is separate from everything else. And we have a, just a code name technology called Madison, which is really the piece that analyzes the data in real time and decides to figure out what we do with that person in terms of putting in the real-time profile. And the real-time profile piece is sort of a key thing for us. So as I said, we have an interesting problem set, because it is not just a big data problem set, but it's also a fast data problem. We got 500,000 requests per second coming in. Now here's the thing, you have to respond back to that ad exchange in under 100 milliseconds. That includes the network latency, which basically accounts for about 10 or 15 milliseconds of that. So you've got 85 milliseconds internally in our systems to figure all this stuff out. But in order for us to be good citizens of this world, we actually give ourselves just under 60 milliseconds to make all these decisions. In 60 milliseconds, we have to load up the user's real-time profile, figure out what it is they've done or are doing, whether we want to bid on them or not, which campaigns they match, whether the campaigns are a good fit, what are the probability of conversion, all that stuff, and then respond back. It's not, that's a lot of stuff. And we touched on this before. Lots of data generated as a result of all this activity, which we need to analyze for reporting and for machine learning. All right. So, just like with every other data problem, when you want to access your data, you can either access it really fast or access it slow. But what you sort of give up in terms of compromise is you either want to have a lot of data, and usually it's pretty hard to access a lot of data really fast, but at the same time, there's more of it. So that's why you have different databases and different systems for different sort of tiers of access. And this is definitely an oversimplification of the process, but we've got the real-time profile, which is used for the RTP and the data collection piece, and then you've got the intermediate piece, which is just for day-to-day analysis, for some of the sort of OLAP type stuff, and also interestingly, when I talk about Aerospike, actually we use it in both tiers for different reasons. And then finally, you've got just the massive amount of data, and usually the way you go over that is with MapReduce. And actually, we have a new open source technology that I'll talk about at the end of the presentation that helps us with that as well. Alright, so this is again oversimplification, but there's a lot of sort of quadrants in the database world that's interesting. Part of this slide from Srini's deck. We use pretty much everything in here actually. So on the sort of top left, you got your classic sort of MySQL, Postgres, OLTP databases. We use Postgres, but we could use MySQL. That is actually our least heavily loaded and kind of least interesting database. So let's put that to the side. Stuff really gets interesting in the top right, where we have real-time databases. Now we have, I'll talk about it in the next slide, a lot of different uses for the so-called NoSQL or key-value stores, or sort of the real-time databases. And actually, there's not one that kind of answers all those questions. You have to use a combination of them for different reasons. And I'll answer as much as I can in terms of how we use these things. Of course, there's a lot of IP data that I sort of can't go into, but we do have a lot of open source contributions in this area, which I want to point out so that you guys can check it out. And of course, on the big data stuff, classic Hadoop everywhere, right? So we're probably the only company in the world that's use Hadoop, us and Nokia, I guess. We use a technology called Disco, which is actually an Erlang-powered MapReduce system. It's an open source project that we also have taken ownership of. We've contributed a lot of interesting features to it. It actually can sit up on top of HDFS, so if you can run in parallel with Hadoop if you really want it. And on the sort of bottom left, we have your sort of analytics databases. Vertica being a really good one, and I'll talk about Hustle, which is our own open source OLAP database that we built on top of our Disco MapReduce system. Pretty cool stuff. All right, stuff on NoSQL databases. You absolutely need them in this day and age for any app that you build. Really, but for our use case, it's critical. It's actually, a simple use case really because most of our users are identified by a single key. So there's not a whole lot of, multiple keys or sort of weird things that need to happen there in terms of the real-time aspect of it. So it's a perfect use case. You look something up, there's data, but it goes far beyond that. So we've tried pretty much every one in existence, and we tried it back in 2008 and throughout the years, and we keep experimenting. But we've ended up 3 or 4 that we actually use in production. Every NoSQL database obviously is different, and they have their own weaknesses and strengths. You got things like Redis, which are great. They have structured data, it's pretty fast, all that stuff. No partitioning, sharding. You have to just make stuff up to really make it, into a clustered database. But it has some really great properties. It can be used as a simple queue system. If you don't want to go into the whole, sort of rabbiting queue type, deal, you can just, fire up Redis, and actually is a way better queue than any of those things for simple queue use cases, right? You are, in some cases, don't want to do any network calls. So any database, any NoSQL database that has a network component to it is just not a good fit. And we use that a lot. I mean, if you have an infrastructure like ours, which has hundreds of servers, and those servers are pretty much, you have apps that are, want to load data in sub-millisecond, a lot of different data, you really can't afford to go over the network all the time. One of the interesting properties of what I talked about, we have 100 milliseconds of network latency, you cut it down to 50 or 60 milliseconds, and then in there you want to make all that complex real-time decisions. Well, you're not just looking up the user information. That is the one piece you're looking up, but then you're looking up all this other stuff, campaign information, budget information, this, that. I mean, there's a lot of elements in that real-time decision-making process, and then you need to load up different data sources for that. You certainly can't be, calling your MySQL cluster there in a you can't even make a network call because even at best, a network call is going to take 2 milliseconds. 2 milliseconds is like, it's an eternity when you're talking about the real-time bidding board, right? So anyway, memory map, local memory map files are great for that. We have an open source project that we contributed to, which is great. I want to talk about one piece in particular, which is our network-backed, sort of network-based NoSQL database we use for real-time profile system. And we had some pretty, as I said, some pretty crazy speed requirements. Well, we needed to be really fast, very low latency, sub 2-3 milliseconds for 99% of calls would be nice. We don't want to deal with partitioning and clustering and all that stuff. With replication, failover, node goes out, it's going to go out. We want it to be fully memory-based because nothing is going to be faster than memory. But we also want it to be persistent, so if the server goes down and comes back up, we want the data to be loaded, so this fast, right? We've tried a bunch of Aerospike 2, back then it was called Citrus Leaf, was the only one that really was able to scale after a lot of the work that we did. So it's fast, so that's good. 2-3 milliseconds, 99% of the time. Yeah, you can hit that in our environment. I mean, it's so funny because you try to do all the load testing in the world. You set up a controlled environment. You set up 50 servers. You hook them all up, and you hit the go button, and everything works great. But then as soon as you go to production, you find things just break on their own, and it's like, hey, I just did all this testing. Well, the real world has a different approach. So Aerospike was good there. As a bonus, we weren't expecting this. We had actually developed our own cross-data center replication to use with the previous technology. It had cross-data center replication. Like, okay, well, wait a minute. If you can throw out a whole subsystem and use one that somebody else is working on, let's do that, and it actually worked. And as I said, we don't have just one Aerospike cluster. We have a couple of them. They have different use cases. One is for more of a, as I said, really fast, 100% memory-based and disk back. The other one is actually pretty cool because Aerospike gives you this SSD back capability where you can, they take over the SSD itself, so that it's not a standard file system, but they actually kind of talk to the SSD itself and kind of figure out a really optimized way of, and let Srini actually maybe sort of expand on my highly technical explanation of that. It makes it a great choice for when you're dealing with more data than fits in memory. And by the way, each of these servers have over 100 gigabytes of memory. And we have clusters of tens of these things. So when I said it doesn't fit in memory, I'm talking over a few terabytes of pure memory. That's when you go to the SSD back system. And that's what that mid-tier data access we were talking, we had in that graph where you have, you don't have the sub-millisecond response requirement, but you want it to be fast, but then you want to put more data in it. You want to possibly put bigger packets in each key, bigger blobs in each key. Aerospike, obviously, very good. Aerospike 2, very good, but it has, a couple problems. Is that there's no structure to the data like Redis, right? So you have to basically put these blobs of stuff there, and in our case, it was compressed JSON, and then happens more. And well, that's great. And that means that every time you want to load something up, you have to transport the whole thing over the network, deal with it, and possibly save something back, and then transport the whole thing back. You're talking about a ton of internal network traffic. And again, at our scale, it just goes crazy. And it works, and it still works. I mean, I still have a huge Aerospike 2 deployment, but we're very quickly migrating to 3, which is a pretty cool system. So good news, still fast. It's still got the failover, partitioning, all that good stuff. But it's got structured data. So int strings, blobs, maps, sets, lists, all that good stuff. And something they call large data types, which are just those 3 things, but for bigger data sets. That's all good, but it wouldn't be any good if you couldn't operate on it. And that's where the UEFs come in. So similar to how you can use lookup with Redis, you can do now use lookup with Aerospike. You can actually write these user-defined functions which execute on the Aerospike cluster itself. The interesting thing there, again, is that you had all the servers sitting there. Those guys have a ton of CPU power that's just doing nothing. Now they're actually doing something, which is great. And as a side benefit, the thing that they were doing a lot, which was transferring a lot of data back and forth in our private network, is actually now doing a lot less of it because all the processing is happening there. You're only sending the chunks of information that is necessary back and forth. So it's good stuff is happening. All right. It also has secondary internet access. We're not using it yet, but it's very useful. Again, in most of our use cases, is a simple lookup by one key, but I can imagine us trying to figure that out. It also has a little bit of sort of a map, kind of an index map reduce built in, so you can actually do aggregation queries. Again, we're not using that. We actually have a use case in mind, but we don't have time to develop it. All right, so we have all this data, and we need to do some reporting on this data. So we're sort of done now with the real-time piece. Now we got these 25 terabytes a day coming in. We have to report on it. We have to give data back to our clients, which is in terms of campaign performance data, right? And we also want to sort of basically, sometimes just very simple campaign performance data, like clicks and impressions and conversions and so on. But sometimes we want to go a little bit deeper and give, sort of more of an insight into their audience, which requires us to do more kind of creative analytics. And we have a pretty big analytics and data science team, which works on all this stuff. One of the things that's important to us is that our own campaign management team, never mind the clients, our own campaign management team, which uses our system and all the data all the time to optimize campaigns, to launch new ones, to pause, to whatever, to maintain them, needs access to the results of campaign performance really fast, and they want to make changes and see changes go live pretty fast. And that's, we're basically able to have our dashboard updated every 15 minutes with the latest campaign performance data. A lot of people in our industry, the good ones are like 4 hours behind. Some of the old school folks are at least 24 hours, which is no good. We also have a whole real-time stream processing system, which I'm not going to talk about here. It's completely proprietary at this point. I am thinking about open sourcing it at some point. There's no immediate thing though, and which actually lets us see stuff in less than 2 or 3 seconds after they happen. So that's actually quite helpful for our engineering team to try to diagnose problems as they're happening. All right, so big data stuff. So stuff's coming in 25 terabytes a day going to a distributed file system, right? So very similar to HDFS. There's a system that Disco ships with called DDFS. Disco is actually an Erlang-based system. So one of the nice things, and it was actually one of those things, when you're a startup and you're trying to come up with your, MapReduce system, you know you're going to need one, in the kind of business we're going in. So your choice is to set up a Duke and, get involved with XML and, or not do that, and just throw a bunch of machines together, install Disco on it, let Erlang take care of all the clustering aspects, and then you just get down to the business of actually doing MapReduce, which is the business, what you want to do. And it turns out Disco was great for that, and there was a lot of growing pains, and we grew with it, and we contributed back, and Disco is a very, very cool alternative to the Duke. One thing it has that the Duke doesn't, in terms of the MapReduce stuff, is it's a multi-stage pipeline. So, it's not just MapReduce. You can do MapReduce, shuffle, sort, reduce, but a lot of different things. And you can actually even have looped pipelines, which is the results of one thing just goes back into another pipeline. So, and that's really great for machine learning. So that's a feature that we've added, and actually in the latest version of Disco. We use it for machine learning. We also use it for ETL. Disco is what powers our ETL system. And the ETL system is simply a MapReduce job to kind of write results back into different kinds of databases, one of which is sort of our Vertica system, which is really pretty straightforward, but we also can feed data back into Hustle, which is our own all that database that I'm going to talk about. Two projects, one we call Inferno, one we call Hustle. Both of those are open source. We go to github.com/Chango. You see all of our open source stuff over there. Hustle. So Hustle is our own column-oriented distributed relational lab database. One of the engineers who created it called it embarrassingly distributed. I couldn't fit on that slide, but it is actually powered by Disco, so it's running on the Disco cluster. We designed it from scratch for our data sets, so petabyte scale data sets. It's column-oriented, so it's very suited well to doing sort of analytics type work, sums and so on. And it's actually compressed. We use bitmap indexes when possible and LZ for compression. It can actually do joins on gigantic data sets. In fact, the higher the cardinality, the better. And it's not a SQL database, but we've actually built a Python DSL that has SQL-like semantics that lets you kind of query this stuff. Interestingly, let me go to the next slide. All right. So there's a couple of interesting, pieces here. Hustle didn't just sort of, it wasn't an idea to just start one day and say, hey, let's build a database. That wasn't our intention at all. We just were solving our own problem and this kind of turned into a database. And I put database in quotes because it's open source. We want the community to use it, but it is definitely not like a packaged product. It has so it's based on LMDB, which is the memory map NoSQL database that you've never heard of. It's actually been part of the OpenLDAP project for a long time. In fact, you can't even find the LMDB source code separately. It's actually part of OpenLDAP. And it's been there for a long time. It's really great. It's very powerful, very fast, and we use it in many different places. One of the NoSQL databases we use across the board. The problem was that it was super buggy in certain scenarios, especially the kind of stuff we were doing. So it turns out we really loved it, so we contributed back, worked very closely with this maintainer, and figured out all the bugs. And it's faster than LevelDB or Kyoto Cabinet or you name your favorite memory map system. It is sort of the basis of how Hustle kind of works. If you're familiar with systems like Impala or to some degree Hive, I guess. I don't know enough about it to really be an expert on that subject. Hustle is similar to those things, except that it's actually indexed, so you can query it pretty fast. Facebook just published a whole thing about how they can, go through 300 petabytes of data and do all that stuff. And they talked about this thing called RC file, which is actually very similar to what we call Marvel, which is based on LMDB. The only difference is that RC file is not indexed, so you have to do a full table scan anytime you want to kind of find anything there. The way we designed Hustle with LMDB is actually that it's indexed. So for certain types of, it's only a kind of a single key, but at least you could actually, it's only a single partition. You can do it whatever you want. But it's definitely way better for doing, if you want to look at semi-structured data and do MapReduce on that. Anyway, I'm not going to go into too much detail here. So it does have types, so you can have strings and integers and so on. And there's actually a meta table that kind of stores some information about this stuff. But the more interesting bit here is this. Okay, let me talk a little bit about the insertion into Hustle, and then I'll show you a sample query and kind of end it there. So one of the problems that we have is that Hustle is optimized for writes, right? It's an append-only system, so you can't update it. You have to just keep appending to it. And it's very useful for certain class problems, like the kind of problems we have. So we can throw petabytes of data at it and query it really, really fast, but you obviously have to deal with those constraints. So we created a system called Marvel, which, as I said, is pretty close to the RC file thing that the Facebook guy was describing. And one big difference is that you can generate these marbles independently of each other in a distributed fashion and then push them into the Disco file system. This allows us to do sort of mass upload of this data into the cluster without having to slow down, to have one single point, so bottleneck, if you will, that causes things to slow down. Now, one big difference between our C file and Marvel would be that Marvel is indexed. So indexing obviously takes time. So if we didn't have this distributed insertion semantics, what we would end up with is, a serious bottleneck where you have to kind of wait there for all the things to happen. So what we ended up doing is actually utilizing Disco's advantage of having this, the DDFS file system. Marbles are generated independently across our cluster, or across our network of servers, and then pushed into the DFS, and then it can be queried that way. Right now, the Marvel format supports CSV and JSON, yeah. So, how do you query one of these things? So here's our Python DSL that kind of looks like SQL, but it's Python. So in this case, I'm looking at the impressions table, selecting add ID and the date. I am using the hustle sum command to sum up the, doing count command. Interestingly, we have the join here. So as you can see, there's a PIX table being used in addition to the IMPS table. The Hustle query optimizer will know that the IMPS and PIX are two different tables, and is using site ID as the key to join these two tables together, and has an overwrite clause, very similar to SQL. When you fire this off, it creates multiple MapReduce pipelines in Disco, and to sort of try to solve it using the query optimizer, run the MapReduce pipelines and bring back the results. Again, one of the strengths of Disco that allows us to even do this is the fact that it has these pipelines. Now, I am not the Disco expert, neither am I the Hustle expert, but as I said, it's an open source project. We're actually going to get PyData in the Valley at the Facebook headquarters next week with one of my engineers who actually invented Hustle. So he's going to be there. If anybody's there, you can stop by and talk to him. Otherwise, we do have a Hustle mailing list and so on. So if anybody's interested in kind of knowing more, you can always go talk to them over there. But yeah, anyway, I think that's sort of really the end of my slides.
Missing parentheses there?
Probably.
Okay.
Probably. I just copied and pasted this from literally one of our first ones. Yeah.
Before we go on to questions, hang on there. First up, I want to give a great big round of applause to Mazdak Rezvani. And just a few other points to note. We are going to give away this awesome 4G social hotspot thing. Just put your card in here. If you don't have a card, I forgot to to mention before, feel free to write it down, write your information down on anything, paper plate, toilet paper, whatever you got, and just chuck it in there. Just pass it around. It'll go around. There's one more here. Okay. So please, by all means. By the way, the actual hotspot is on, and it is a social hotspot. So if anyone wants to connect to it now, it should work for the first 100 megabytes for free. So you should be able to all connect to it, hopefully, if it's working. So that's the first thing. The second thing is, if everyone could kindly take out their smartphones, photograph this event, and post it to the Meetup page. There's an option with Meetup that lets you post photo. Anyone who's RSVP can post a photo. So please just pull out your phone, snap away, post it up. And let's start. First question. You had your hand up. Yes.
The query example that we gave, is it running in real time, or this is for the middle tier of it? You have one-time question.
Yeah, so that's a quick question. So is this query in real time or is it for the middle tier? This query is actually for the lower tier. This is for the big data sets. Interestingly, with Aerospike, and I'll let Srini answer that, there is a way you can do queries in the middle tier, and Srini will.
Mazdak actually talked about Aerospike 3.0. One of the things that we've done since I last spoke here in 2012 is added a bunch of secondary indexes and query-based access you can do on Aerospike. The challenge there was essentially to make sure that the existing performance on key value stayed as it was, even after we added new features. And we, I think, have achieved that, actually proved that. And basically, we can do arbitrary SQL-like computations using Lua functions and aggregation. And we have a pipeline, much like what Mazdak described, except the loop. You don't have a loop. This is one way because the database does to finish. So you just get all the data. Now, when you run a query or a secondary index, what happens is it goes into the way secondary indexes are implemented is we kind of co-locate it with all the primary indexes. So what that means is it is well optimized for what is called low selectivity queries, where a query of the secondary index will return multiple rows. Then you go to each node, query sent to every node, and then in parallel data is fetched into the system, and each node performs some level of processing. It's basically pushing processing close to the data. And then once that processing is done, there's a certain output which is emitted, and all of the resulting data from the output on each of those nodes. The final phase, it happens in the client by fetching all the data from each of the nodes, and then you get access to query.
Next question.
What about the system architecture? You design the system as based on performance?
Now, I guess I should put a word, the caveat on the word real time, because real time bidding, it's pretty fast, but real time you mean it's, less than 100 milliseconds, right? It's not in the same definition as sort of the, real time OS or anything like that. That said, we didn't, obviously we use a lot of SSDs wherever we can, and the architecture of the system itself, in terms of how it's laid out, is definitely optimized for that purpose. However, we don't have any special hardware. It's commodity hardware that we use for this.
How come we use Python for the stuff? Python is single thread and multi-thread.
Yeah, that's a good question. Why Python? Why use Python? Python is single thread, probably not the fastest thing on the planet. There's a lot of different languages involved. There's actually a whole lot of C involved. There's a bunch of Go involved, and there's Python involved as well. Python is great at writing code really fast, so for a lot of the business logic here, we use Python. There's a lot of C involved in the lower tier and Go involved in the middle tier, so yeah, it's across the board.
Can I add, Chango was the reason Aerospike did a Python client.
Yep, and since then we've actually referred to using the C client because
All the way to the back. So just some reflection from you.
A little louder, please.
Yeah. NASDAQ has a matching engine, right?
yeah.
And so orders come in, they match, and then results go back. So here, just trying to understand what you're saying. So this is more of a architecture question.
Sure.
The database question. So you're saying the IP site information, key information is collected some processing on this, and you send it out to your 15 or 20 or 80 customers, and one of them says, I'm going to purchase this, and you take his data, then send it to...
Okay, all right, no, it doesn't quite happen that way. So, I guess it's more of like a business model question as opposed to... And so what happens is that we have a data partner network. So we have publishers that we have given our JavaScript to, and these guys are sending us interesting data anonymously, obviously. It's just a cookie ID and a bunch of information coming in, and we store that in a central place. We also have advertisers that have the actual similar pixel on their site. Now, this is not a requirement for advertisers, but many do because they want more customized ad delivery. So that stuff comes in. So can you imagine all customer information sitting in our network, in our sort of data center, without data centers actually. And by the way, one of the things that's really important when we talk about this is the cross data center replication, because everything we have has to be imported from data centers, and it has to be fairly quickly synchronized. But it's sitting there, and when a bid request comes in through an ad exchange, right? So you're viewing an ad, the ad exchange says, "Do you want to bid on this person at this time?" All they send us is the cookie ID. They don't send any other information. I mean, they send what site they're on, maybe what site the ad they're looking at, obviously, otherwise we won't know what ad to render. We then look up that person's information in our database. If we have any information about them, then we kind of look at it and say, okay, what kind of information do we have? What do we know about them? What don't we know about them? And then with campaigns match, we want to show any ads. And then when we say, we respond back to the ad exchange, all we say is that here's an ad tag, go ahead and render it. We don't send any customer information back to them. All we send is the ad tag, and they just render the ad tag, and the ad tag contains our click tracker, our impression tracker, all that stuff, so we get information about what ads are
Wait, hang on. First up, everyone will be here for one-on-one questions at the end, so I'm sorry I didn't mean to stop your question, but they will be here. Let me just get through other people and come back. Yes?
I just want to get a sense of the degradation of performance when you reduce the amount of hardware that you're using. So if you take something with, let's say, half the amount of memory or half the number of cores, but you double the number of machines, what is the degradation in performance? Is it linear?
That's a really good question. And it depends on which subsystem it is. There's many different subsystems. In certain subsystems, with the RTV subsystem especially, you really, let's see what happens if you just increase. You could definitely increase the machines with lower power, but it turns out, with the way hardware is these days, to get like a 32-core machine is actually, instead of getting, two 16-core machines, it's cheaper to get a 132-core. And it scales fine. So the number of, some apps are CPU bound, some apps are IO bound, and it really depends it depends on what kind of subsystem you're talking about, and they're all bound by a different aspect of the system. In many ways, it really is hard to say, but if it's CPU bound, then, one machine with many CPUs is just as good as many machines.
Right, that's linear, but if it's IO bound, it's not going to be linear.
No, then you're, exactly. If it's IO bound, then you're, must distribute across. Yeah.
I'd like to add to that one point. From a database point of view, this is actually a very interesting thing that we have noticed, is because Aerospike has built this, what I would call SSD-based optimized access. We are about 100 times faster than traditional databases, even an order of magnitude faster than other NoSQL systems. And now that we have that, what customers are doing is they take 15-node clusters which they deployed. It's actually, there's a case study with Intel and Applex that's published. Applex's clusters started growing over the 3 or 4 years they were with us. Then last year they decided to go to a more higher capacity machine with parallel SSD. I think they put 15 or 20. The case study has it on our website. And therefore reduced the cluster size from 50 or whatever to 12 or 10. I don't remember the exact numbers. And that increased their headroom with better management characteristics and so on. So this is actually a real problem at the database layer, which because the way you have to do it in such a way, and this is kind of the way I think about it myself and at Aerospike is, we really care about vertical scaling as much as we care about horizontal scaling. And if the product does that, then customers then have an option based on what is the sweet spot hardware, and then they can deploy these systems, which are both cheaper, as well as in terms of cost, as well as deployment complexity.
Also fail-safe too.
And thanks for how long is getting in the book.
Yes.
Sure. As you're ingesting so much data every day, how do you have to monitor or adjust both the logical structure of where that data gets stored and also the clusters themselves? Do you have to grow the clusters over time, and if so, how do you monitor that?
Well, that's a good question. We over provision, obviously, so we don't have to grow the clusters. But that's another thing about, that's one of the requirements for. So especially on the NoSQL side with the Aerospike specifically, right? We actually add nodes not that frequently, but we do add nodes, and the automatic replication takes care of the fact that it's so now it just starts doing the migration, and then slowly those things become accessible in a different node. It is again, Aerospike, that problem happens most frequently with the Aerospike cluster, and thankfully it's built in. With our Disco cluster, as Disco has a similar thing built in. We often add 5, 10, 20 nodes at a time, and it has a different replication mechanism, but it does take care of that as well. But that happens, yeah, of course.
Time for just like 1 or 2 more questions. Yes?
So I understood from your last comment that you probably have your own data centers. I wonder, why don't you use some kind of cloud services like AWS or?
Well, so we have we use a managed hosting solution. Why don't we use AWS? I'll tell you, even in the managed hosting data center with physical servers, with dedicated switches, we had so much traffic, we had to ask them to move us into our own dedicated rows and our own dedicated room. The amount of internal traffic I talked about before, all of these servers talking to each other, with lots of data packets going back and forth, it crushes the best of the internal networks. So we have dedicated switches that's not shared with any other clients, dedicated rows, dedicated everything, and that's just the nature of real-time bidding. But if I was doing any other app, I would have to use AWS or something else.
Last question. Yes.
You talked a little bit about the hustle architecture,
Yeah.
and it wasn't really clear, and I'm not familiar with the product, but you said that it was based on Disco. So does it work with Disco supplied public APIs? Is it an extension of Disco? Is it written in Erlang? What's
All excellent questions. So it is built on top of Disco that uses 2 features of Disco. It uses the distributed file system to store the Marvel database files, and it uses the Disco multi-stage pipeline MapReduce to actually go through them and basically do the query execution. Disco, in essence, it's pretty neat because it's not written in Erlang, it's written in Python actually. Hustle is in Python. Disco is pretty neat because what happens, and this actually makes it, especially if you're using it in Python, it makes it really easy to do things that otherwise would take a lot of work. So if I want to run a MapReduce job, I write a Python function. I mean, obviously you create the internal project to kind of extract all that out. But you create a Python project. Essentially what it does is that it marshals that Python object, that Python code, in the sort of the pickle format. I don't know how many of you guys are familiar with Python, but Python code can be marshaled and sent across the network. So instead of actually having to deploy code to your Disco cluster to run it, it just takes literally the bytecode, sends it over the network, and executes it. That is one of sort of the interesting features of Python and Disco working together that we utilize for Hustle as well. There's some cool stuff in there. I mean, it is only version 0.2. But we do use it in production ourselves. And Tim, the guy who created it, is very passionate about the subject matter. And GitHub.com/Chango, if you ever get in touch with him, he'll be more than happy to walk you through some scenarios.
Okay, before we go on to the raffle, I just want to first give a great big round of applause. Mazdak, will be here to answer more questions for one-on-one after the raffle. If anyone did not get a chance to drop your card in the raffle, now is the time. Where is the raffle container? What? I hear people saying right here. Well, where is it? Right here? Oh, and we have more of these screen wipes up here. Yeah, I know. Just pass them back. And now, for the Karma Wi-Fi hotspot. How about you? Sorry. Reach in, mix it up. Look away and grab out a card. Read it.
Near Pengus?
Near Pengus? That is you. You won. Congratulations. You might have
I was trying to get the mine. Make my work out.
Thank you all for coming.